Hi guys, once more. This one pertains to an earth dam. So this was also requested by a certain student. So an earth dam, guys, is when you've got a water table, okay, that you feel you can identify in your plot, and you just get a TLB, or maybe you just want to have a dam from rainwater. Get a TLB to just dig a very big hole for you, and then water just flows in after rain and for runoff. So in our situation here, we've got a dam, a natural dam, which is just a hole in the ground. Now, our natural dam has got a leak at this point. So your farmer asks you, can you please build a wall, a concrete wall for me here, so that I prevent water leakages in this point. So basically, instead of having now earth only, which is your natural soil, you're having something called a reinforced concrete wall. Okay. Now, in walls, we like to do what we call a buttress. A buttress wall is something like this part over here. Because if this is your water, this shape is very stable to the point that water cannot just push this. But this you will learn when you do centroids or but in DBS. There's something called slenderness. If this shape was just a normal vertical wall, it's easy to so that it can slide and collapse. But it's got this shape, so it's reinforceable. It's stronger than just a single wall. Okay, that's a buttress wall. That's what you call a buttress wall. So in essence, that's where you will be building the buttress wall. It's like 100 meters of it to prevent the leakage. Okay. The dimensions for this wall go as follows. The wall will be 100 meters, okay, long. And from your external dimensions, it will be 6 meters at the bottom. And then at the top here, it will be 4 meters, okay. Your thickness of your walls is 1 meter each. Each thickness is 1 meter. We got a hollow section here. They want to be able to put in pipes to control water levels of the dam. They need to put a valve over there so that they can open it to channel out water across. So there might be a pipe that gets to the full point of the capacity of your dam. Then you can have someone to go into this opening section and open a valve, then it takes water out. Okay. So in this instant, our internal dimensions here on top, from here to here, we have 2 meters. Then from here to here, we have 4 meters. Okay. This is what I was trying to allude to the student who asked me this, that first thing you do in this case, you identify the shape of your base. This shape, what is this? This is a trapezium. Okay. Why is it a trapezium? It's got two parallel sides that are equal and two parallel sides that are unequal. When you have two sides parallel that are unequal and two that are equal, first thing you do, you need to get the middle distance, the middle dimension. Okay, how do you do that? If we name this L1 and this we name this L2, we say L1 plus L2 divided by 2 gives you this length over here. And if you go to the formula to calculate the area of a trapezium, it says area is equal to L1 plus L2 divided by 2 times height, the perpendicular height, which is this one, which is 6 meters. Okay, guys? So I'm saying to the student, what you need to do is to first calculate this object as if it is not hollow. It is a full solid trapezoid. Okay? So, first of all, you need to calculate the base. Right. Let's go about that. The base of this, first of all, we need to say L1 plus L2 divided by 2 times height. Our L1 is 4 meters, L2 is 6 meters. That gives us 10 divided by 2 is what? 5. 5 times 6 becomes 30. square meters. Okay, guys? So that's the basis of how we are getting to our square meterage. Now, if you go to your module where you've got your constants, okay, there's a note here that says, note, if height is multiplied with answer, the volume is obtained. But where is that? Where are we told that? We are told here where you use a constant to calculate area. Meaning that if you have an area and you want the volume, you just need a third dimension, which is height. So in our case, we calculated area, the area of this, by saying area is equal to L1 plus L3 divided by 2 times height. And then we got it, that is 30 square meters. But now we want volume. So we multiply by the length, which is 100. That gives us 3,000 cubic meters of concrete. Okay, guys? I just want to go to the page in your module guide to show you the formula of a trapezium. Okay? Remember, guys, square meterage is two-dimensional, but cubic meters is three-dimensional. This is page 38. On page 38, you've got something like this. This is for a trapezium. Okay? If you look here, we are getting the midpoint area to calculate. So here's the formula. Area is equal to L1 plus L3 divided by 2 times height. That's what we are employing in our situation here. Okay, guys? So here we get 30 square meters times 100 meters to get 3,000 cubic meters. Okay? And then there's the middle area, which is hollow. We need to calculate that volume that needs to be deducted from our overall calculation. And that one we know from internal dimension, we have 2 meters, and then at the bottom we have 4 meters. So we say 2 plus 4 divided by 2. So 2 plus 4 is 6. 6 divided by 2 is 3. 3 times 4 is 12. Then you say times the height or the length. So that's 12 square meters times 100 meters. That gives you 1,200 cubic meters. Okay. So that's where we get that we should deduct the internal volume. So we say 3,000 cubic meters divided by 1,200 cubic meters. That gives us 1,800 cubic meters of concrete. That is for walls and floors. Okay. So guys, now we go to the next portion of our exercise, which we are required to calculate with the mixed design. We are given a bulking factor of 20%. Okay, there's the bulking factor 20%, and we are given a mixed design of 1:2:4. Okay, it will always go like this. Cement will always represent 1, sand is the next one, stone will always be the last one in the factor. Okay, guys, I showed you already an exercise where I did this thing. So you need to add up your ratios first of all. 1 plus 2 plus 4. What does that give you? 7. So we say in cement, when calculating cement, say 1 part of cement divided by 7 times our bulking factor. Our bulking factor is 20%. But we're not going to purchase 20% of material. We need 100% of the original volume plus 20%. Hence we say 100 plus 20 to give us 120% times 30.3 bags of cement per cube of concrete times 1,800 cubes of concrete. That gives you 9162.72 bags. But since we do not have a supplier that will sell you 0.72 bags, we round that 0.72, 7.2 to a whole number. That means we're going to say 9163 bags of cement. Okay, guys? Go to sand, same thing. 2 parts of sand divided by 7 times the bulking factor. 120% times 1,800 cubes gives us 626.40 cubes. Okay, and then stone, the same thing. 4 parts of stone divided by 7 times bulking factor times 1,000.